White dwarfs are one of the most intriguing types of celestial objects, representing the final evolutionary stage of stars that were once similar to our Sun. Their history and understanding span several centuries, intertwining with the development of modern astrophysics. This comprehensive account delves into their discovery, physical characteristics, formation, and significance in the cosmos, providing an in-depth understanding of white dwarfs. Discovery and early observations. The story of white dwarfs begins in the 19th century. The first white dwarf to be discovered was the companion to Sirius, known as Sirius B. In 1844, German astronomer Friedrich Bessel observed that Sirius, the brightest star in the night sky, exhibited a peculiar wobble in its motion, suggesting the presence of an unseen companion. It wasn't until 1862 that Alvin Graham Clark, an American telescope maker, confirmed Bessel's prediction by visually detecting Sirius B. Sirius B was significantly dimmer than its primary companion, Sirius A, yet it had a comparable mass. This discrepancy in brightness and mass led to puzzlement in the astronomical community. By the early 20th century, it became clear that Sirius B, along with a few other faint stars, did not fit the traditional star classifications. In 1914, American astronomer Walter Adams took a spectrum of Sirius B and found it to be of spectral type A, similar to Sirius A, but vastly fainter. This was a critical clue, suggesting that Sirius B was incredibly dense. Understanding stellar evolution. The path to understanding white dwarfs was closely linked with advances in stellar astrophysics. By the early 20th century, astronomers had begun to develop a clearer picture of how stars evolve. They realized that stars derive their energy from nuclear fusion processes in their cores, converting hydrogen into helium. In 1926, British physicist Ralph H. Fowler applied the newly developed principles of quantum mechanics to propose that the high density of white dwarfs could be explained by electron degeneracy pressure. According to quantum mechanics, electrons cannot occupy the same quantum state, and this exclusion principle, known as the Pauli exclusion principle, creates a pressure that supports the star against gravitational collapse. Further advancements were made by Indian astrophysicist Subrahmanyan Chandrasekhar, who in the early 1930s calculated the upper limit of mass for a white dwarf, now known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. Chandrasekhar's work demonstrated that stars with masses above this limit would undergo further collapse, leading to neutron stars or black holes, rather than becoming white dwarfs. Physical characteristics. White dwarfs are characterized by several unique physical properties. Density and composition. White dwarfs are incredibly dense. A typical white dwarf has a mass similar to that of the Sun, but a volume comparable to Earth's. They are primarily composed of electron-degenerate matter, with cores typically made of carbon and oxygen, the end products of helium fusion. Temperature and luminosity. When they first form, white dwarfs are extremely hot, with surface temperatures exceeding 100,000 K. However, they lack an internal energy source and gradually cool over billions of years. As they cool, they become less luminous and move down the Hertzsprung-Russell diagram, eventually becoming black dwarfs, though the universe is not old enough for any black dwarfs to yet exist. Formation of white dwarfs. White dwarfs are the end state of stars with initial masses up to about 8 to 10 times that of the Sun. The formation process involves several stages. The main sequence. Stars spend the majority of their lives in the main sequence, fusing hydrogen into helium in their cores. For stars like the Sun, this phase lasts for billions of years. Red giant phase. After exhausting the hydrogen in their cores, these stars expand into red giants, burning hydrogen in a shell around a helium core. Subsequently, helium fusion ignites in the core, producing carbon and oxygen. Planetary nebula and white dwarf formation. When the helium in the core is depleted, the outer layers of the star are ejected, forming a planetary nebula. The remaining core, now devoid of fusion reactions, becomes a white dwarf. This core is primarily composed of carbon and oxygen, with some stars potentially forming neon and magnesium cores. Importance in astrophysics. White dwarfs play a crucial role in various astrophysical contexts. Cosmic chronometers. The cooling rates of white dwarfs allow astronomers to estimate the age of stellar populations. By measuring the temperature and luminosity of white dwarfs in a cluster, scientists can deduce the cluster's age. Progenitors of type S supernovae. White dwarfs in binary systems can accrete matter from their companions. If a white dwarf approaches the Chandrasekhar limit, it can undergo a runaway fusion reaction, resulting in a type Ia supernova. These supernovae serve as standard candles for measuring cosmic distances due to their consistent peak luminosities. Galactic chemical evolution. White dwarfs contribute to the chemical enrichment of galaxies. The planetary nebulae formed during their transition phase release heavy elements into the interstellar medium, fostering the next generation of star formation. Observational techniques. Studying white dwarfs requires advanced observational techniques. Spectroscopy. Spectral analysis provides insights into the composition, temperature, and magnetic fields of white dwarfs. For instance, the presence of heavy elements in a white dwarf spectrum can indicate ongoing accretion from a companion or interstellar medium. Astrometry. Precise measurements of a white dwarf's position and motion, as done by missions like Gaia, help determine distances and proper motions, aiding in the study of stellar populations and galactic dynamics. Photometry. Monitoring the brightness variations of white dwarfs, especially in binary systems, can reveal details about their size, mass, and the nature of their companions. White dwarf varieties. White dwarfs are not a homogeneous group. They exhibit a variety of characteristics. DA and DB white dwarfs. These are classified based on their spectral lines. DA white dwarfs show strong hydrogen lines, while DB white dwarfs display helium lines. This classification helps in understanding the surface composition and evolution of these stars. Magnetic white dwarfs. A subset of white dwarfs have extremely strong magnetic fields. These fields can influence the star's spectral lines and are thought to originate from the progenitor star's magnetic field. Pulsating white dwarfs. Some white dwarfs exhibit pulsations due to instabilities in their interiors. These pulsations provide a window into the internal structure and composition of the star through astroseismology. Future of white dwarf research. The study of white dwarfs is poised to advance with upcoming astronomical missions and technological developments. Next-generation telescopes. Observatories like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, will offer unprecedented resolution and sensitivity, enabling detailed studies of white dwarf atmospheres and their cooling rates. Gravitational wave astronomy. Binary white dwarfs are expected sources of gravitational waves. Missions like the Laser Interferometer Space Antenna, ELISA, will detect these waves, providing new insights into the binary interactions and merger processes. Exoplanetary studies. White dwarfs offer unique opportunities for studying planetary systems. Observations of transits and debris around white dwarfs can reveal the fate of planetary systems after the host star's death, shedding light on the ultimate destiny of our own solar system. Conclusion. White dwarfs are more than just stellar remnants. They are key pieces in the puzzle of cosmic evolution. From their discovery and the development of quantum mechanics to their role as standard candles and cosmic chronometers, white dwarfs have continually enriched our understanding of the universe. As we advance our observational capabilities, The study of white dwarfs will undoubtedly continue to reveal new and exciting aspects of astrophysics, offering deeper insights into the life cycles of stars and the dynamics of galaxies. Thank you for watching. Please subscribe our channel.